Welcome to this Chapter 39 video, Part 3 of 3, where I talk about system APIs for directories and for metadata. So, let's talk about directories really quick. You cannot use the same open and unlink that you can for files. In order to work with directories, you need to use system calls specifically designed for directories. In this particular case, to make a new directory, we use mkdir, or makedir. It takes a path and it takes a mode, the mode being what you want the permission bits to be set to. When you create a new directory, several changes are made. The first is 2 directory entries are added to the subdirectory you create. The first directory entry is the single dot directory. The single dot directory is very odd in that it is actually a directory entry pointing to the inode of itself. So if, let's say, this new directory has an inode of 5, that inode of 5 will be set for the single dot directory. The double dot directory is also added to a subdirectory when it's created. The double dot directory refers to the inode of the parent. We use these two to help us do things such as if we want to change to the parent directory, if we want to basically make our current working directory the parent directory, we can type cd ... and it will change to the parent directory. If we want to run a program within the current working directory, all we need to do is specify the dot directory slash and the executable program name, and that program will be executed. The other API is the rmdir API, which removes a directory at a particular path. Again, this is like unlink, but what this does is actually goes through the process of removing the 2 directory entries and the directory itself from the file system. Now, here's one thing to be aware of. You cannot remove a directory if there are other directory entries other than the single dot and the double dot. If it has any other files or directories, this will produce an error if you try to remove the directory, which is fine. You're not deleting files. But there are things you can do to remove files and directories recursively. The rm command, Linux rm command, can be run with the -r option. If you specify the -r option, what it's going to do is it's going to walk through all the files and directories and subdirectories and files in them until everything is deleted. Delete those things. Once it's done, then it will go ahead and delete the actual directory itself. Please use this command very carefully because you can destroy an entire file system by deleting a directory recursively. Now, if I can create directories and I can delete directories, how do I actually access directories from my program? Well, there is a system API called getDents, G-E-T-D-E-N-T-S, get directory entries, where we specify a descriptor that we received doing an open. We have a buffer and a size where we can fill that buffer with directory entries. But frankly, this is fairly complicated and it can be rather error prone. So we have a standard library that provides 2 functions that we can use. The first is the opendir. Opendir allows us just simply to specify the path of the directory we wish to open. Opendir will return what is called an opaque pointer. An opaque pointer just simply means you won't be doing anything with that particular structure. It is hidden to you, but you don't need to do anything inside the structure. You just simply use the pointer as what we call a reference, a stream reference or stream handle. So you use this stream handle within the read directory API. Read directory takes this particular stream directory handle and will produce directory entries one at a time within that particular directory. There's a nice little structure that's defined here. This is not an opaque structure. We can actually access members to it, and there really is only one entry that matters to us, and it's called dname. D_name is part of this directory entry structure and is the actual file name that we can use within that particular directory. Do understand that this is just a file name. There is no path associated to this particular file name. Any path that needs to be created needs to be done programmably by you as a programmer. So something to be aware of when it comes to file metadata, every file has a certain amount of data that is not part of the actual file data. When I create a text file and add text data to it, or I create a source code file and add source code to it, there's metadata that I do not see associated to that file. So every file has a certain number of file links. There's always at least one file link. If the file links go down to 0 because of the unlink command, then that file is deleted. The file links for this particular file identify how many directories are linked to that file. You always have one for a particular file, but you can create multiples for a file. When a directory is created, we have 3 links. One from the parent to the child itself, one from the child to itself, and one from the child to the parent. All of these links are created. So every directory that's created has at least 2 links to it immediately. And the parent directory has a new link added to it when we create a subdirectory. You can see this whenever you take a look at a particular file system when you create a directory. So let's take a look and see what we can see with a particular directory. I'm going to go ahead and go to the console just briefly, and I want to show you something inside this console. So right now I have the XV6 file system. This is the source code directory that you've been working in. I'm going to go ahead and create a new directory using mkdir. I'm going to call it temp. Actually, before I do that, I want to run a command called stat. If I type stat and use the single dot directory, remember this references my current working directory, you'll see that this particular dot directory has one link within it. So let's take a look what happens if I go ahead and do make directory temp and then perform stat again. So stat and the single dot. Oh, and it didn't create it. So I'm going to have to revise what I do. Let's take a look inside temp. If I do stat of the current directory, you can see that it actually has 2 links here. One link is coming from the file system, or coming from the parent directory, and the other link is coming from the single dot. I'm guessing I didn't see a link increase here because the directory is in a mounted state. I'm not exactly certain why, but let's try again. I'm going to make a new subdirectory called foo within temp. Now if I do stat for the current directory, you'll see it now has 3 links. And if I do stat on foo, it has 2 links, one from the temp directory and one from itself. So you can see that this link count is keeping track of all the directories that all the points where it can be found as a directory entry. You also have metadata for file times. There's specifically 3 file times that we deal with. There's an access time for when the file was last accessed or read. You have a modify time for when the file was last written to, and you have a change time for when the metadata for a file was last modified, such as file permission or ownership, or the links will also cause the change time to happen. The metadata for file and directory permission bits is also fairly important. So every file and directory have permissions, and you've seen some of these already. There are three primary permissions: the read permission, the write permission, and the execute permission. For files and directories, the read just simply means we can read the content of that file or directory. Write means we can modify files and we can add directory entries to a directory. But execute has a little bit different meaning. For the execute bit on files, it means that we can load and execute that particular file. But for directories, it just simply means it allows a directory to become a current working directory, meaning we can change into that directory as necessary. There are some special bits that we can work with. There is a set UID. This allows a particular file to be executed, but the process, user ID and group, or user and group, are actually changed to the file's owner. So if I am user John and group support, but the file is owned by Chad and group develop, and I execute that particular file, then the process will run under Chad's user ID and the develops group. We call this the set UID. There's also a set GID that is actually used by the directory. So if I create a file in a directory without the set GID, it actually, that created file gets the same user ID and group as the process that created the file. With the set GID bit set, it actually causes files to be created in a directory that have the user and group IDs of the directory owner. So that's a bit different. Without set GID, it's the process owner that gets set within the file metadata. With set GID, it is the directory owner where the file is created. And then finally, there's a sticky bit. You'll hear this referenced every once in a while in the Linux system. Basically, if a sticky bit is set, then there are certain directory entries that cannot be modified by other users. So if I've got a directory that I have write access to, but it has the sticky bit set to it, and there's another file or directory from another user, I am not allowed to actually modify that particular file or directory because the sticky bit is set. So again, permissions apply to the current running process. It all depends on whether or not the process has a particular user. User rights are applied when the file owner ID matches the user ID of the current running process. Group rights apply when the primary group of the process, when the file, it is the primary group of the process, or both the primary and secondary when the file is accessed. So if a file is created, the file is assigned the primary group of that user. When a file is accessed, the rights apply for both primary and or either primary or secondary groups when the file is accessed. But this is only true if the user rights do not match. And then the other rights are applied if neither user or group rights matched. So we talked about this in the files, but this applies to directories as well. You can read file and directory metadata using the stat API. The stat API actually takes a pointer or a reference to the struct stat. This structure actually contains several elements. All of it comes from the metadata that is stored on a file system. Some important ones are the inode. Inode is the unique identifier of that particular file. Mode. Mode is the file permission bits, those 9 bits, including 10 bits if you include the special bits. The metadata also includes the user ID and group ID owners of that particular file. It contains size information, so you can actually know how many bytes of the file are there. There's also time information. One thing I did not include on this list, which is kind of hard to describe, is it actually contains information about the blocks used in the file system for this particular file. So you have blocks, you have the number of blocks or the count of blocks, and then you also have the size of each block. So let's say I have 8 blocks set aside for a file, and the block size is 4K. So I'm actually going to switch over to the console so we can take a look at this. So I'm in a directory called temp. I'm going to go ahead and create a file. Let's go ahead and name it bar, and I'm going to go ahead and put some data into it. So echo data in the file, and I'm going to send it to bar.txt. If I take a look at this, there is bar.txt. I can display the content by typing cat, and it shows me the data in the file. So let's use stat to take a look at the statistics of bar.txt. Now this is very interesting. We can see the file name is bar.txt. It has 17 bytes in it. But it also shows me that that the file occupies 8 blocks in my storage, and each block is 4K in size, meaning that for 17 bytes, there's actually 32 kilobytes set aside for this particular file. Now, why is that? Well, Linux is actually anticipating that I'm going to add more data to this file eventually, and in order to keep things from being fragmented too much, it's just pre-allocating blocks that it believes I'll use sometime here in the future. Here's the inode number for that particular file, 3409776. And right now, the directory, the temp directory that you see here, actually has one link to this particular file named bar.txt. If I want to create a second, maybe I want to call it foo.txt, I can go ahead and call the ln command, do bar.txt and foo.txt. Now, if I take a look at stat for bar, you'll see that there is 2 links, and that the directory now contains both files, but they're pointing to the same data. If I modify data, so let's go ahead and echo more data and append it to foo.txt. If I take a look at bar.txt, it actually now contains the data as well. And you'll see, whenever I do bar.txt, that there's more data in the file. I haven't increased the block count because it made reservations for that, and it is still the same inode. Other pieces of data are the access right. So 644, 6 being the user rights, 4 being the group rights, and the second 4 being the other rights. And it shows it in an ASCII format as well. Here is also the user ID and group ID of my particular file system. And finally, the access times, such as when it was last read. In this case, it was read just a little bit after I modified the file. When was the last time the metadata was changed? Well, the last time the metadata was changed was the last time I wrote to the file. If I go ahead and link, again, bar.txt to text.txt, and take a look at this, you'll see that access and modify have not been changed, but now the change time has been modified because all I did was modify the metadata, adding a brand new link to this particular file. So let's go back to our slides. You can actually reference this particular data within a program by allocating a structure, a stat structure. Here I've declared it as variable st, and then pass a reference to that variable into the stat function along with the path of the file you want to get information about. This brings us to the end of this Chapter 39, Part 3 of 3 video, where I talk about system APIs for directories as well as for metadata.